Welcome. In this lesson, we're going to introduce some of the concepts behind graph theory. So graph theory is probably not exactly what you thought it was unless you have actually had an introduction to this before. But let's start off by imagining the following network of friends. Suppose Diana gets a solid case of the flu. So here's Diana. Each vertex or node in the network represents a person. So we have 1, 2, 3, 4, 5 vertices, or you could say you have 5 nodes in this graph, in this network. So each of these nodes represents a person, and each edge between them, so that's this straight line, represents a friendship between the two people it is incident to. So we say that a edge is incident to 2 nodes or 2 vertices. 2 vertices that are connected are said to be adjacent. So in this is an example of a graph where a graph really is just a structure that consists of nodes and edges. So anywhere there are relationships of some sort, we can represent the entities of that network with vertices or nodes. And we can represent connections between those nodes with edges. So assuming each person only makes contact with one other person during his/her contagious period, is it possible for Diana to spread the flu, ultimately to everyone in the circle? Well, that could be the case, because if we think about it, Diana could make a contact with one of 3 people. So if Diana makes contact with Anne, now Anne gets it, and if Anne gets it, suppose she contacts Elisa, who makes contact with Carl, who makes contact with Bob, and so as a result, that disease will, or that sickness will spread to all of them. And without loss of generality, we could have said Diana gives it to Bob, who gives it to Carl, who gives it to Elisa, who gives it to Anne. So you can imagine that even with with 5 people, and each person only making contact with one other person, that disease can still spread. So this is an example of a graph, and by definition, a graph is a finite meaning that it's not infinite, a finite non-empty set of vertices, V, and another set consisting of edges, E. So one of the things that we know is that sets describe many important structures in mathematics, and these sets keep track of the vertices and edges. A complete graph is one in which all vertices are adjacent. So we can think of a graph where we have that. So for example, if we only had 2 vertices, this would be considered a complete graph, because every vertex connects to every other vertex. And if I added a third one, as long as I connected that third vertex to every other vertex, this would be a complete, sometimes we would call this K3, or not K parenthesis 3, but this would be K3. That's the notation we use for a complete graph with 3 vertices. K4 would look kind of like this. We'd have 4 vertices. I'll just draw them as a square, and as long as every vertex connects to every other vertex, then we would have a complete graph. So this would be K4, a complete graph. A graph does not have to be complete. This is just a special type of graph where every vertex, this is the most dense type of graph you can have, where it's the maximum number of edges that you can possibly gain. So in this case, having 1, 2, 3, 4, 5, 6 edges is the most that a graph of 4 vertices can have, provided that we don't do things like have loops or have multiple paths to get to another adjacent vertex. So let's go ahead and take a look at our example. Here we want to describe V and E. What is one way to do this? So one way to do this, and everybody's going to have a slightly different notation. I like to keep it pretty as simple as I possibly can. So if I'm going to describe the set of all vertices in this particular graph, I'm just going to label them A, B, C, D, E for Anne, Bob, Carl, Diana, and Elisa. So those are my vertices. This is a complete listing of all of the vertices in that graph. Now the edges, and I have to be kind of careful here, maybe I should call this, a lot of times the edge set is written kind of more as that symbol, And so the edges, there's a lot of ways we can list these. We can either label all of the edges, but that's kind of redundant because we can specify an edge by describing the two vertices that are incident to that edge. So for example, this edge here would be AB. This edge here would be BC. So maybe I should check them as I go. So that one. Then I have the edge between B and D. I can check that one. By the way, we do not need to list BA, CB, and DB because the network goes both ways. There are other types of graphs that are called directed graphs where there's an actual arrow of flow of information. So there might be situations where Bob shares information with Carl, say on Facebook, but Carl blocks Bob from seeing what he's doing. So we have BD, and then we also have these three edges. So that would be AD, and then here we have AE, and finally we have CE, which is that edge right there, or EC, it doesn't matter which way we list those. So that's a complete description of this graph. Now, there's many ways I could draw this graph, and I'm here my vertices are actual pictures of people, but you see up here, they're just dots, and typically we list them as dots and lines, but this was just a fun interactive example. So this is one example of where we could see graphs, and other examples are the internet, the web. The entire web is a graph where items are documents and the references, or the links, are connections between those documents. So when you're talking about the World Wide Web, it's a gigantic graph of information. Networks. A network consists of sites that send and receive messages of various types. So you have a site represented by a node, and then you have edges connecting them, or you have links between two sites that represent the edge that connects those two nodes. Program structure. So whenever you're talking about coding, a compiler builds a graph to represent the relationship between classes. The items are classes. Connections are represented by possibility of a method of one class to call a method from another class. So very sophisticated stuff, but the simplicity of a graph. Street network. So intersections are vertices and edges are roads. Social networks, like the one we saw up here. People are vertices and edges represent friendship. Disease networks. Diseases are vertices and edges are connections between the diseases. So, for example, you might associate certain types of cancer with other types of pre-existing conditions, and having a big graph to represent them would be very valuable. Now, I highly encourage you this will really kind of set the frame and set the mood. This is a really fun, interesting documentary that it's about 45 minutes long. It was put on by BBC. It's called 6 Degrees of Separation. And it actually deals with Kevin Bacon, the actor, who this whole idea of 6 degrees of separation started with, essentially that the distance between any two people in the entire world is no more than 6 people apart, meaning that by having a friend of 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 a friend, I can basically, in that way, relate myself to anyone in the world. Some now argue that 6 degrees of separation is now less due to the internet, and something like more like 4 or 4.3 the last I heard. So some properties and by the way, in this whole lesson, we're just sort of defining things, getting used to terminology, because there is a lot of it. It's a whole new language that we have to learn. So the degree of a vertex is the number of edges incident to that vertex. So and essentially, another way of rephrasing this is how many vertices emanate or originate from the vertex, and you count them, and that's the degree. For example, the degree of Anne is equal to 3 in the example above. So if we look at Anne, we see 1, 2, 3 edges, essentially saying she has 3 friends. Or excuse me, she has 3 friends: Elisa, Diana, and Bob. So here's another example. If we create a small graph, a little sample graph, and we just list these 3 vertices, and we connect them maybe in this way. We call this vertex A, B, and C. We could say that the degree of A is 2 because there's 2 edges coming off vertex A, and vertex B has a degree of only 1 because there's only 1 edge coming off of vertex B, and the degree of C is also 1 because there's only one edge coming off of vertex C. Now, there are different types of travel that we can perform on a graph. Whether that actually represents physical motion or not is irrelevant. When we're talking about traveling, for example, even in this graph, I could travel from Anne to Carl by way of, say, Diana, Anne to Diana, Diana to Carl. Now, I'm not physically traveling to that person. This is not how far they are spaced apart. This is just an arbitrary sketch of how they are related. So when we talk about travel, it does not have to mean physical travel. Although in the example of streets and intersections, it could mean just that. So there are different types of travels, and the simplest type of travel is a path. And a path is a walk from one vertex to another vertex in the graph. So if I just arbitrarily make up some vertices here, and I'll just label these A, B, C, and D, I can, for example, let me just put one more edge right there. One possible path, and we'll just go ahead and list these out as you can either comma separate them or just list them together. So one possible path would just be AB. Okay, a path is just a walk from one vertex to another vertex. A, B, A would even be another path. Doesn't have any specifications on where it has to start or stop. So A to B back to A would work. We could go A, B, D, A, C. And we could do A, D, B, D, C, A. Essentially, there are I shouldn't say infinitely many, but yeah, there are infinitely many because we could go A, B, A, B, A, B, A, B all day long. So there are really infinitely many paths that you could take in this network. We want to start placing some restrictions on these paths because a lot of times we don't want to just start and stop at random places. So we have a definition for what's called a circuit. And if you think about like an electrical circuit, a circuit starts at the battery. If you've ever seen a circuit before, it starts at one end of the battery, and then there might be some sort of resistor here or something, and then we close that circuit. So we started here at the battery and we end our wire at the other terminal of the battery, but still at the battery. So a circuit is a path that starts and ends at the same vertex. A path has no restriction. A circuit is a path, meaning that it's just a travel from one vertex to another, but you have to end at the same vertex you started at. So we have to get more specific with circuits for this network up here. So for example, if we started at A, one possible circuit would be A, B, D, A. So notice that our first and last vertices are the same. We could do A, B, A, D, B, A, A, D, B, A. So we can traverse this graph. We often use the word traverse. A traversal is just a route. We could traverse this graph from clockwise, counterclockwise directions. We could even have other path circuits like A, B, D, C, A. We could have A, B, D, B, A. There's just so many circuits, but the restriction is it's a path that starts and ends at the same vertex. Now, we have another type of constraint, and we'll see why these would be valuable, why it's important to talk about cycles and circuits and paths. A cycle is a circuit. So basically, it's a path that starts and ends at the same vertex where all vertices and edges are distinct within that path. So for example, A, B, D, C, A would be a cycle, and if you think about cycle, you just sort of think about the fact that it forms a loop. So A, B, D, C, A. That forms a perfect cycle, right? And then we could go around that cycle over and over again, just like a washing machine or a dishwasher. And we just have to make sure that we don't hit the same vertex twice. So like a possible circuit would be A, B, D, B, A. But this would not be a cycle because we reference or we hit the same vertex twice. And actually, in that case, not only do we hit the same vertex twice, but we also take the same edge more than once. So when we go from A to B, down to D, back up to B, we've basically traversed this edge right here twice, and then when we go back to A, we've traversed that edge twice. And the cycle says it's a circuit where all vertices and edges are distinct within that path. So for this one up here, we could have A, B, D, C, A. That would be one. A, B, D, C, A. So it's a circuit, and it happens to also have the characteristics of a cycle. We could just have A, B, D, A. That would also be a cycle. And we don't have to start at A. That was just an arbitrary choice. We could have done C, D to A to C. C, D, A to C. And so when you're looking at these, you can tell right away that all of the edges and vertices are distinct because we don't ever arrive back at the same vertex again. So that's a cycle.